Okay, I'm going to talk now about the conservation law. And this governs the rate of fluid flow through a closed solid or closed body. So if we have a volume and S is the surface enclosing that volume, and the fluid has some velocity v, then the rate of change of the mass in v, so I'm going to be really casual with my notation here, mass, the derivative of mass with respect to time, it's actually equal to a surface integral and the surface integral will involve that velocity, and there will be two more components here. There will be a rho. This was essentially going to fix your units. Correct, because velocity is meters per second. There's no mass anywhere. And then finally, we'll have a negative sign. And that's because this is going to be, this accounts for the fact that velocity usually indicates leaving the surface. So, and this is actually, it'll be called the rate of inward flow. And the rate of outward flow is actually going to be minus this. So it'll just be that rho v dot ds. No minus sign. So let me unpack all of this to including that minus sign. So let me start with why is it ds? So why is it a ds and not a dv? That's not an obvious thing, because the velocity field is actually defined for all of this. It does not just need to be on the boundary a priori, but it turns out, here's the idea. The particle motion on the inside does not affect the total mass. So to give an example, if you have just a single particle and over a time dt, it moves over here, then the mass at our original time is actually equal to the mass at our new time. Right? And that's because the particle stayed inside. So therefore, only particles at the edge matter. So this is exactly why we have a surface integral. So in other words, that derivative, we know it should look like a surface integral of some function for this reason. So the next question to address is why is our integrand, why does it actually look like this velocity? And this thing, of course, this is called the mass flux. And you should compare it with the electric flux, and we'll be talking about a heat flux. This is really all a related concept. It spans different fields, surprisingly. And so now the real question is, why is this V here? And the whole point is that for a fluid, the velocity is the only reason. particles could leave. Our region. And this is actually a physical assumption, right? Like, for example, if you're boiling a pot of water, then particles could escape by evaporation, but that's different physics than what we have in this case. So let me just talk about really quickly how particles leave with velocity. So, for example, if we look at a single particle and it has velocity v, it's at the edge, then after you move some time further, the particle is actually on the outside of that region. So our mass has actually decreased. And this corresponds to that velocity. So the velocity is the factor, but why is there that dot product? Why is the normal vector involved with this? So let me just illustrate this by, let's suppose this is our boundary. Or you can just think of this as S. So let's suppose S is kind of flat. And so now I'm going to have two particles. One particle is moving to the right. So after some time dt later, the particle is outside. And notice that v dot n is greater than 0, because n is pointing in the same direction as v. So v dot n measured the escape of the particle. On the other hand, if the particle is going down, then after some time dt later, the particle is actually down here. It didn't go outside. It's actually still inside. And in this case, v dot n is actually equal to 0, and there was no escape. And you could also have inflow, right? You could start with a particle on the outside, and if the velocity is negative, oppositely oriented, normal vector, then after our time dt later, the particle is inside, starting from outside. And in this case, v dot n is less than 0, and there was a capture of the particle. So to summarize, v dot n it measures the escape of the particles. And this actually accounts for why we have that annoying minus sign here too, because why the minus sign? So if escape happens, then the mass will decrease. So therefore, dm dt would be less than 0 in that case. And so to get a positive thing, we need to add a minus sign. So in other words, minus dm dt, this would be positive. And this would be equal to v dot n. So now you just move that minus sign over, and that accounts for that. And I think the last thing we need to mention is, why is there that rho? Can we unpack why that's there? So this is just dimensions. So on dimension grounds, the left-hand side is kilograms per second. Right? This is d mass dt. And the right-hand side, well, it's a surface integral. Let me just recall it for those who forgot. So the right-hand side is rho times meters per second times meters squared. So overall, it's rho times meter cubed per second. And so our choice of density, of course, is mass divided by volume, so kilogram divided by meters cubed. And we have the desired cancellation of the dimensions. So rho is the right choice to be there. If we didn't have the rho, it would not correspond to dm dt. That's why rho is there. Okay. Thanks for watching.